196. 2 times 10 is 20. 20 times 9.8, 196. Now, let's go back to this table that hopefully you've drawn in. So if the kinetic energy is 0, and the position alone tells you that the gravitational potential energy is 196 joules for this liter bottle of water. Now, if you add up those two energy values, you get 196. And my wonderful students, that is what we call the total mechanical energy. And the symbol for that is capital E by itself. And it's just the sum of whatever kinetic energy you've got and whatever GPE you've got. All right? And theoretically, you can calculate if you have enough to get one altitude, whether it's 10 meters or 4 meters or some other meters, you can figure out all the other energy values at any level that you like. So make a note of that. It's kind of like a crossword puzzle. If you know GPE and the KE, you can figure out E, total mechanical energy. And then once you get total mechanical energy, that's going to be the same for every altitude. So for instance, just before impact, let's go all the way down to the bottom. Y equals 0. So just before impact, all of that potential energy way up at 10 meters, it's now kinetic energy. All right? So all of that 196 joules is converted over to kinetic. And guess what? MGY, or I should say minus MGY, is 0, because Y is 0. And so just before impact, those are the two values. But hey, guess what? Energy, total mechanical energy, E, is still 196. And so you can actually figure out any kind of a table of values of energies that you would like to do. Now, I want you to set up this table, and what we're going to do right now, since we don't have any clicking, I'm going to do a document cam diagram or table with you. We'll work out a few of these babies together. And I'll use Derek, could you help me with this up here? Can you turn the lights all the way on for now, just for that? Okay, what we're going to do, go ahead and copy down this table and see if you can leave a little bit of room to roam, a little bit of room for writing extra calculations. And what we're going to do is use the Talking PDF technology here. And we're just going to work at a little bit of the table just to show you how it works. Okay. And let me pause the podcast. Come on, clicker. Here we go. Okay, now we're back to this table. And, let's switch over to the laptop. Okay, so now we've filled in a bunch of these things. Tonight, you're going to have homework 7.1. And it's going to be a table kind of like this, except it's a basketball, not a liter bottle of water. 0.800 kilogram special basketball. But you're going to be working out stuff in this. Now, why do I call it homework 7.1? Because it was supposed to be in homework 7 and I forgot. So but this one I've set it to be, I think, 6 attempts, because you're going to want to practice really carefully with it, especially the very last one. And it's due the morning of the next midterm. So this is like a study assignment. So just go ahead and use it a few times. Use it to study, and hopefully, you get some points off of it. It's a good. There's a couple other things in there besides this table with the basketball, but this is a good start. And usually the second midterm, I'm usually going to ask you a table question, because these energy levels are going to be important for us when we study atoms and electrons. For atoms and electrons, atoms and molecules, and the electrons that bind molecules, or the intermolecular forces, or the interatomic forces that bind molecules together, is basically because of the behavior of electrons. Those electron energy levels are extremely important for us, and they're going to be electrical energy, not gravitational potential energy. But everything that we have done here today with this gravitational energy table, we'll be able to do with electrons orbiting the nucleus of an atom. Now, questions before we continue? Raise your hand if you'd be in favor. Wait a minute. Raise your hand if you want to pick up your exam printout. Nobody? Okay. You guys that haven't got your exam printouts, we got them up front here. And I'll be able to give them to you, because I think we're going to dismiss early today. Maybe. But not yet, because we got to talk about angular momentum. We're going to march forward into chapter 5. I saw this guy over here. Oh, yeah, Dr. B. And then, oh, not another chapter. This is a cool picture. It's one of my favorites. It's a very excellent astronomical observatory down in the in Chile, up in the Andes, called Paranal. But these are each of these things are big, huge telescopes. They're not domes, but you can see this one over here is open. This, you can't really see it here, but I suppose on the YouTube you'll be able to see it. That's that second one in from the left. You'll be able to actually see the telescope, the opening of the telescope. Fantastic place. Anyways, look at those star trails. Those star trails seem to be curving across this time exposure, but really the stars aren't moving that fast. It's the Earth that's moving and makes the stars appear to move like that. And so that state of spinning that the Earth has, and the apparent circular motion of stars, we're going to start talking about that. So we're starting around page 64. I start with this picture of two objects being levered. The block of stone on the left being leveraged by a lever, and the block of stone on the right is the fulcrum. And let me spell that for you. Fulcrum. And that's about page 64 that I start talking about all this stuff. So leverage and torque. Here's another leverage situation. A couple shrimpy little kids on a teeter-totter, seesaw. And in this particular case, you can tell who's the bigger kid. It's this little boy. And why is that? Because his end of the teeter-totter is down. And they're both sitting about the same position. But because the little kid is heavier, he exerts more torque. So this idea of torque, T-O-R-Q-U-E, It is the rotational analog of force. These little kids, they're not doing any, they're just rotating a few degrees clockwise or counterclockwise as they play on the seesaw. You know, they're going up and down. They're having a nice day. But since the distance, and this is this diagram is directly from your textbook, the distance PL, ideally on a seesaw, is the same as the distance RL or RP. All right. Now, if you cheat in, you can be defeated. If the little boy cheats in a little bit and gets a little bit closer to the pivot point P, the fulcrum, he can be blazed up by his little sister. His little sister can win. But if they have equal positions, the weight force of the son and over here the weight force of the daughter, I made it a little bit smaller. Okay. So this combination, here's another way to look at this. If this thing could not pivot, in other words, if it was up on two blocks or two posts, two supports, and it couldn't pivot, there'd just be a net force downward on this teeter-totter equal to the weight of the two kids. But because it can pivot, it can spin about this particular point P, you can develop rotational motion. And so let's just start talking about torque. And just a reminder, this is in chapter 5 now. The torque you develop depends on your position. How close are you to the pivot point P? Katerina. And how many newtons are you pushing or pulling? In the case of the little shrimpy kids, it's just a weight force. But if you've ever worked on some equipment and you take your wrench and you try to get your wrench to torque your bolt, get your bolt tightened or untighten it, loosen it up. So it depends on how much, it also depends on the angle at which you exert your force. So here's another diagram from the textbook. And this is for a door. And you don't even think about this, but I'm forcing you to think about this particular thing. If you exert a force in the direction of this hand, the fingertip, point in the direction of the force, okay, vertically upward, and if this is the hinge over here, H, then you're going to get maximum torque on the door. And if you're going to open a door, that's how you do it. Because if you do a force like F2, forget about it. You're not going to get any torque. You get zero torque. If you push straight at the hinge, well, you might move the door toward the hinge by a millimeter or two if there's a little bit of give, but it's not going to open the door. So you never want to do this if you're opening a door. All right, so, and I'll just instruct you now to read in chapter 5.5. I have a little bit more geometric discussion about this angle, the different angles that you use to push on things to achieve torque. Here's some vocabulary terms. The two words translational and rotational. Now they are different. And there's a couple diagrams here. Translational motion means going from point A to point B. Either as a straight line or maybe in a curved trajectory. The curved trajectory is a combination of two translations, some translation up, some translation across. Rotational motion means you're not going anywhere, but you are spinning. So actually, an object in rotational motion has some 1/2 mv squared, if you think about it. Because each little pixel of mass, each little molecule of wood in the piece, so these are like rulers that you're looking at. Every molecule of wood in this ruler has a little bit of mv squared, 1/2 mv squared. But it doesn't have a lot of motion. Its actual velocity vector is constantly changing. And it never gets any further away from the center of mass, in this case. And so it's got 1/2 mv squared, but not because of the fact that it's being pushed along a delta x. It has 1/2 mv squared because it's had some torque that's caused it to spin. Now, translational over here, this is delta x is a translation. Delta y is a translation. Delta z is a translation. All right? And when you have an F delta x translational motion, yeah, you're going to have some 1/2 mv squared because you're moving from point A to point B, from one point on the x-axis to another point on the x-axis. All right? So those are two vocabulary terms I want you to keep in mind, and they are in the textbook as well. I use the word translational to refer to momentum, and I use angular or rotational to refer to spinning or rotational motion. Now, the very most important concept for us in this chapter, chapter 5, is angular momentum. And it turns out that angular momentum is another dynamical quantity that encodes the spin state of an object spatially, even though it might not be moving from point A to point B. It is subject to a torque, and the torque changes. There's a lot of delta P's from a force, but you might actually get a change in the angular momentum state. So the thing that the momentum that a torque changes is called angular momentum, and that's what we're going to be talking about. So there's translational or linear momentum. That's in Newton's law, delta P over delta T equals F net. And then there's angular momentum. And this formula here, where lowercase Greek tau stands for the torque, that's going to be the change of angular momentum. Right now, in this formula, it's a question mark, delta something, delta question mark. That means, what is it? This is what we're trying to figure out. What kind of rotational analog to a momentum is changed by a torque? And I've already given you the answer. It's angular momentum. And there's actually two kinds of angular momentum. It's kind of cool. And really, you shouldn't really say there are two different kinds, but there's two different ways to account for angular momentum. First of all, there's orbital angular momentum, and that's for any object on a curved path about a central point. So you could think about the angular momentum of a planet going around the sun. It's on a curved path, and the sun would be the central point. The sun is the source of the force that keeps that planet on its orbit. And then the other one is the spin angular momentum. So the object is spinning, but it's not spinning around a central object, but it's spinning on its own axis. And usually a spin angular momentum is for something that's spinning about its an axis of rotation that goes through its body and directly through the center of mass. Now, in Chapter 5, there's a discussion of how to locate the center of mass for an object. And the center of mass, what we do visually in Chapter 5 is what an engineer would do with a lot of measurements and a lot of calculus to figure out the position of the center of mass. So let's focus on orbital angular momentum states. So as I said, it's relative to some fixed point, for instance, the sun. So go ahead and draw a picture of the SUN. And here's the Earth down here in the lower right, and this kind of green big circle here represents the sun. Did you know that the sun, the brightest color of the sun is actually green? It's kind of cool. So that's why whenever I draw the sun, I make it kind of look kind of green on the slides. And here's the distance r. That's a factor in the angular momentum. You could be doing the same thing and study the angular momentum state of a comet going around the sun. And there's a lot of astronomers, or planetary physicists they call themselves, in our department that work really hard on comets. So they have to know the angular momentum state. Because the angular momentum state tells you a lot about the solar system, actually. So the thing that you want to figure out is the distance or angle from that point, that central point, i.e. the sun, out to the planet or the comet. And I've drawn a vector from the sun out to the Earth. I didn't draw one for the comet there on the elliptical orbit, but you could do that if you want. And it will have a different value for r. And as a matter of fact, a comet on a highly elliptical orbit like that has a range of r. It has a minimum r, has a maximum r, and it's constantly changing because it's on an elliptical orbit. Now, Earth's orbit is actually a little bit elliptical, but it's pretty close to a perfect circle. So we'll just kind of round it off and call it a circle for today. And then the other thing that factors into the orbital angular momentum is the velocity. So go ahead and draw a vector for the velocity down here. And if you are up above the solar system toward the North Star and looking back at the solar system, you would see everything going, almost everything going counterclockwise. Everything spins, almost all the planets spin counterclockwise, and almost all the planets and many comets go counterclockwise around the sun. Now the formula for the angular momentum on a circular orbit is just this. Capital L, angular momentum, is equal to mRV. So whatever the mass is, multiply by r, and multiply by v. And if you have eyes to see, this is similar to the torque. The torque is really the product of the position and the force. Okay, so a small force and a large distance from the fulcrum, a large r value, gives you a lot of leverage, even if you don't have a lot of force to apply. That's why Archimedes, the great mathematician, said, if you give me a lever long enough and a place to fix it, I can move the entire world, which is true. No matter how big something is, you can leverage it if you have a long enough lever. And so this formula here for angular momentum might be reminiscent of that. What is r times mv? What is mv? That's momentum. So the angular momentum is r times the regular momentum. Torque is r times the regular force. And there's a bunch of geometry, but on a circular orbit, you don't need any trig. It's just m times rv. Okay, so that's orbital angular momentum. Let's take a look at spin. So here's an example of a millstone or a grinding stone spinning 600 RPM, 10 times a second, on an axle. And really, the spin angular momentum is just the sum of a bunch of orbital angular momenta of every pixel of mass of this millstone here. So just pixelate this, mentally pixelate it, and then figure out MRV for each of those pixels and then add them up. But here's the interesting thing. For a rigid object, they're all going at the same angular frequency. So that means angular frequency. Ooh, I should have written that angular velocity. Okay, write angular velocity there. And for this, angular velocity is 600 RPM. How many rotations per minute? So for angular velocity, which is the rotational analog to delta x over delta t. For rotational velocity, or angular velocity, it's just how many spins per second, or in this case, how many revolutions per minute, how many RPMs. And you could convert that into degrees per second if you want. You can convert it into degrees per year, or any other way of measuring angular speed. Now, I'm injecting a new vocabulary word, moment of inertia, and it is something that I want you to read about in Chapter 5. Your homework is to read up to Chapter 5.5, as well as homework 4.1. And in Chapter 5, you will learn about the moment of inertia, symbolized capital I. For a spinning object, like this millstone, there is a fixed value for the moment of inertia. The moment of inertia, capital I, is like the rotational analog of mass. But it is defined in a very unusual way, but it works out really nicely. And you'll be able to read about that in Chapter 5. And the the spin angular momentum formula is simply I times the rotational velocity omega. So make sure here in item 6b, instead of writing angular frequency, make sure you write angular speed or angular velocity there. And omega, this lowercase omega up here in the formula, looks like kind of like a curvaceous W. That is omega. That stands for the angular velocity. So think about it again. Regular momentum is m times v. In this particular case, angular momentum is rotational analog of mass times rotational analog of velocity. It's moment of inertia I, which you'll read about in Chapter 5, times omega. And you'll read a little bit about omega in Chapter 5. Now, there's one exception that we don't understand, and that's electrons. They seem to have intrinsic angular momentum, but we don't think that it's because they're spinning. They just seem to have it. I mean, you can think about an electron spinning, and the spin angular momentum of an electron is basically where magnetism comes from. It's weird. But, and the orbital angular momentum as well. They both have magnetic effects. But electrons' intrinsic angular momentum, we don't know where it comes from. Same thing with photons, the basic particle of light. Every time you look at a star at night, on a clear night, your retina is gathering just handfuls of photons per second, but from that star. But it's still enough for your brain to register as a point of light. So here's the diagram. This shows omega, angular velocity omega. For every rotating body, omega is the same if it's a rigid body. So 2 points on the object at different distances from the axis of rotation, they may have different speeds, delta x over delta t, but they won't have different angular velocities, omega. Right. So I'll dismiss you now. We're a little bit early today. Homework 7.1, and definitely read up through chapter 5.5, and we'll have a ton of homework on the weekend for chapter 5. You're dismissed. Come on up to the front if you want exam printouts.